All right, now we'll continue our discussion. And by the way, in our stress strain curve under the tensile test, we have this curve, right? And this is the strain, the vertical axis. I mean, the vertical axis is the stress, and this one is the strain. And in this region, this is what we call the elastic region. And mostly in our computations, we only will only consider this. Okay, we'll only have the range of loadings in this, or the analysis would be limited to the elastic range. And also the slope of this linear line is what we call the modulus of elasticity, symbol E. I mean, the symbol used is E. This is the modulus of elasticity, or sometimes referred to as the Young's modulus, or elastic modulus, which is simply a measure of the of something related to the stiffness. So if you recall in our strength deformation curve, right? So this proportionality constant is called stiffness. Okay, so force is directly proportional to the deformation, and this proportionality constant is what we call the stiffness. Right here, when using the stress strain curve, because we said that if we divide this force by the area and we divide this by the length, then we get the stress strain curve. Okay, so right here, when we apply the Hooke's law, it's expressed as the stress is directly proportional to the strain, except that this one is referred to as the elastic modulus, and this is only applicable in this region, in this elastic region. Okay, so if we reach this other region, then we would need a different type of analysis. Okay, and also I would like to point out that different materials will have different stress strain curves. Like for example, brittle materials, sometimes they just have something like this, a non-linear, and then it just breaks up to this point. They don't have this plastic behavior. Okay, what else? And I think let's move on now to the compression test. Okay, so compression test, this is usually done for brittle materials, like for example concrete. Okay, so concrete, they have more strength in compression than in tension, because the tensile, let's say the strength of concrete, for example, is 21 megapascals. Its tensile strength is just something like 10%, 8 to 12% of the tensile of the compression strength. So that means it's just around 2 megapascals for the tension. So that's why for brittle materials like this, they are tested, or they are utilized for compression. Okay, so it's just the same testing machine, and we have this, for example, this is the base, and then we have this test specimen right here, and this test specimen is being subjected to axial compression, or to compression loadings until it breaks. Okay, and the shape of the stress strain curve, and take note, this one is stress, but this is compression, right? So just take note, this is compression, and this is of course strain in the compression. Okay, so it was noticed that the curve for a concrete is something like this. Okay, so you would see that it has different curves than that of the steel in tension. Okay, so there's also a maximum, something like a maximum compressive strength in this graph, and you can also we can also interpret this that depending on the grades of concrete, like for example, you have a higher grade, then you have higher strength, so probably something like this. But if you have a lower grade strength, lower grade concrete, then you have a lower you have this curve. Okay, and it just means that if you have some curves like this that has more strains, right, it has low capacity or low strength, but the strain is it can accommodate more strains, and that means that it is more or it has something like a ductile behavior rather than high strength concretes like this. And by the way, they should be at some strain value. I mean, they all meet at the same strain value right here, the maximum. Okay, so for higher grade concrete is more it is less ductile. It has no ductile behavior as compared to this lower grade concretes, but the strength is higher. Okay, so that's one thing. That's one example of this compression test, and there are still many more, like for example the flexure test. Okay, so flexure test, recall that we have this test specimen, and then it's subjected to flexure loadings. Alright, so this is the flexure loadings, and let's say we have the support right here. So this is often encountered in the design of beams. Let's say for the reinforced concrete beams, it's the most common test would be the flexure test. And what else? I think I have to explain one example right here. So let's say this is a reinforced concrete beam, and if we cut a section, what we see is this concrete plus the reinforcement, steel reinforcements. Okay, so if you have this test, then you can also have this output. I mean the stresses or the loadings and the deformations. Okay, so one example is the moment curvature diagram. Right? So this one is moment, so that means it's load, and this one is curvature. So in terms of I think this is in terms of rotational deformation. Okay, so right here it's like this. So once you load the beam in flexure loadings, okay, so both the concrete and the steel carries the stresses. Then at some point it will break. Because concrete has lower strength and tension, then it will break. Somehow it will break. Okay, and then in this tension zone it will break. So at that point it's only the steel reinforcements that will carry the tensile stresses, and then it will have this deformation, something like this, and then it will break. Okay, so the point here is that whatever test we do, there's gonna be or we can plot it out in terms of the forces and deformations or stresses and strains. Okay, and then last one, we can also have test in terms of, let's say, torsion. Okay, for shafts and mechanical components. Okay, so now let's move on to the stresses, fundamentals of stress and strains. Now, what is stress? We have been talking about stress, and stress is basically a function of internal forces and the geometry or geometric parameters, because sometimes it's not always the area parameters. So when you say geometric parameters, this includes area or moment of inertia or the polar moment of inertia. Okay, and this one, when you say internal forces, this refers to the if it's actual internal actual force, or the torsional, or torque. I think torque would be a better term, torque or moment. Okay, so this is the stress. Now for me, I describe stress as a force distribution, although in some other references, I've I've read that they describe stress as a unit strength of material. But for me, I just describe it as a force distribution. And when we say distribution, then that's where the geometric parameters comes into play. Okay, so the basic unit of stress is pascals for metric systems, and pascals is just simply Newton per meter squared. But for English, this is PSI. It's just pounds per inch squared. So take note of the value. This is Newton, a unit of force, and this 1 meter squared, this is a unit of area, right? So force all over area. Okay, but as I have always said, that it's not always the area. I mean, even if it's moment of inertia or polar moment of inertia, but when we apply all the parameters and the variables, then we get into this unit, Newton per meter squared, or pascals. Okay, so what's the difference between pascals? I mean, this is stress and the pressure. Okay, so let's write here. What's the difference between pressure versus stress? Okay, so any guess or any answer? Okay, so for example, we have a tire right here. So this tire, this is being inflated by air, right? So you introduce air here, and because of that air, there's gonna be a pressure. And pressure, in terms of fluid mechanics, it's the forces that's perpendicular to the surface area. Okay, so now what is stress? Because pressure has the same unit as the stress. Okay, so when we say stress, this is internal. So let's take a small portion of the tire right here. Let's say this is the pressure. This is external, right? This is external. But if we want to check the internal force distribution right here, the forces right here, right, in this material or inside the material, that's what we call stress. And this one is pressure. Okay, so now let's move on. Another handy unit is the use of megapascals, because Newton is very, very small. I mean, it just it's a small value. So sometimes it's often expressed in terms of, I mean, the stresses is sometimes expressed in terms of megapascals, because sometimes the area that's considered is sometimes it's just millimeters squared. Okay, so one megapascal is equal to 1 Newton per mm squared. Okay, so take note of this conversion, because this is a very handy conversion. Okay, and also recall that when you say metric, when we use metric, then of course the prefixes comes into play, like for example kilo times 10 to the 3, or the giga, or milli, or things like that. Okay, now for the English units, we have this PSI is equal to pounds per inch squared, and sometimes it's also common to encounter the term KSI. What is KSI? That is kips. This is kips. And what is kips? This is just simply kilo in pounds. Okay, kips per square inch, right? So this is kips per inches squared. And of course, if sometimes it's also possible to encounter, instead of using inch, it uses feet. It uses feet squared. Okay, so now let's have this figure in our lecture handouts. Okay, so the concept of stress, as I have already mentioned about the Cauchy concept of stress, that if we have this material right here, let's say this is just an arbitrary body. This is not a peanut. This is not a peanut. This is just an arbitrary body. So let's say we subject this arbitrary body with external loadings, and we cut a section. So once we cut a section, then we expose the internal forces. So right here, there's gonna be one. Let's say there's gonna be a resultant force. Okay, internal resultant force. And if we have this plane right here, and let's say we are using a rectangular coordinate system, and it's something like this, right? So this is the cut section, and we have this resultant force, and we can describe this this resultant force. And as you notice, this is a three-dimensional problem, or this is a three-dimensional picture. So this means that it is it can have a component along the XYZ, or the S, T, and N, which means that the N is the normal direction and S and T are the axes along the parallel or along the plane of section. Okay, so we recall that for Cauchy, he introduced that stresses are not just normal, but also there's there's also stresses along the parallel direction. Okay, so overall, this is the resultant forces. Okay, and right here, so in our lecture handouts, if we take the limit of the normal force, okay, and I mean, if we take the ratio of the normal force to the area, and we take the limit of area, or if we shrink down the area to 0, that's what we call the normal stress. And for this one, for the shear, then we can also have this stress, that's the shear stress, and we can have also the shear stress along the other direction. Okay, and for the shear stress, Cauchy also derived the relationship between this one, the stresses, because this is the complete picture. This is the normal stress, and we have this shear stresses, and you would notice that this shear stresses is the same as this one. It just says here that, okay, let's check if we can zoom in. Okay, so you would notice here that we have shear stress YZ, so that is the shear stress in the direction of Y, but in this plane that is perpendicular to Z. This one is shear stress in the direction of X, but in the plane that is perpendicular to the Z. Okay, and he derived that this shear YZ is just equal to shear in this ZY, shear ZY. Shear YZ is just equal to shear ZY, or shear ZX. Okay, so these two right here, they are equal, and then these two right here, they are just equal. Now this is three-dimensional, but if we want to, sometimes we just consider two-dimensional. So this is how it will look like. Okay, and another terms that's also that we'll also encounter is we have this. Sometimes the loading is just purely along one direction, and that's what we call uniaxial, because one direction. But sometimes we can encounter maybe in the stress transformation topic we'll encounter biaxial stresses, so meaning two directions. We have this direction and that direction, and we can also have triaxial. Just simply means we have XYZ directions. Okay, so what else? Okay, so now let's talk about the strain. Okay, so strain is can be described as the deform or deformation is a function of deformation and its original geometry. Okay, so it is described as the relating to the deformation and the original geometry. Okay, and if we'll consider extensional strain or a normal strain, that's just simply the deformation or if we have this actual loadings, then of course because of these loadings, then this one elongates. Now this elongation is what we call the deformation, and this one is the original length. Okay, so strain is deformation divided by the original length for this specific specific situations. Okay, and deformation is measured in terms of length, right? So let's say this is meter or millimeters, and this one is also in terms of length. So that's why the unit of strain is sometimes dimensionless. However, sometimes it is expressed in terms of percentage or in microstrains value, or the ratio of, let's say, inch per inch, something like that. Okay, so for strains, then of course it is there's going to be a strain related to the normal strain, and there's also going to be shear strain. Okay, so normal strain, that means that the strain is along the actual directions, but this one is because of the shear loadings. Okay, so right here in our lecture material, we have right here in figure 2-15. So for example, this is my original body or original geometry. So if I load this along the x direction, that means I have a uniaxial loadings, then the deformation, it will elongate along the x direction. Okay, so that's what that's the normal strain or extensional strain. Now if the loading is in y direction, then the strain would be in the y direction. If it's in z, then it's going to be the z direction. Now if the loadings, they are all combined x, y, z, then it's just simply a combination of this strain in x plus the strain in y plus the strain in the z. And sometimes if we consider the thermal effects, then there's going to be of course expansion of the material, then we have to take that into account as well. Okay, now for the shear strain, it's like this. Now because of the shear loadings, then we have this kind of deformations right here. Okay, so it's more on angular deformations, although as I have always said that this if it's in angular, or if it's described in terms of angular deformations, we can relate that to the linear dimensions as well. Okay, now what's the relation of the stress and the strain? So we have here the Hooke's law. We have here the generalized Hooke's law, that the stress is just simply directly proportional to the strain. So if this is in x, this must be in x. If this is in y, this may be in y. And the proportionality constant right here is the modulus of elasticity. Okay, another one right here. Now for shear, it's almost the same, because shear is just equal to the modulus of rigidity times the shear strain. Okay, so this is the relationship, that the shear stress is directly proportional to the shear strain, but the proportionality constant is letter g, and this g is referred to as the modulus of rigidity. Okay, this one is rigidity, the other one is elasticity, modulus of elasticity. Okay, so I guess that's all, or we still have another concept right here, the concept of Poisson's ratio. Okay, so what that means is that if I have a uniaxial loading, if I elongate this material in this direction, there's what it says that there yes, we have an elongation in this direction. We have an elongation, but in this lateral direction we have a contraction. Okay, so something like this. I would like to show you some figures from the textbook by Beer, Johnston, and Day Wolf. And this is actually one of our reference materials for this course, and we have the 4th edition. Okay, so here in page 51 there is a figure of the test equipment right here, and then the test specimen. So the test I mean the test shown here is a tensile test. Okay, so in this test specimen, you would notice that there is a threaded ends, and this is usually for metals. Okay, so it has a threaded ends, both ends. So that's where it is being gripped by the holders or the grip in this equipment. Okay, so it's being pulled apart, and then there is a measuring device in the middle that measures the strain, and that measuring device is called the extensometer. Okay, so depending upon the material, whether it's steel or maybe it is aluminum, or even if it is a brittle material, it will have a different stress strain curve. Okay, so right here in this figure right here, this is a stress strain diagram or stress strain curve for a low carbon steel. Okay, so you would notice that the curve for a low carbon steel is different from the curve of aluminum alloy right here. Okay, so starting from this point, and then it will have a rupture right here. And you would notice also that there is a this is the ultimate tensile strength, and we have this the sigma y. This is the ultimate. I think I should rather zoom this in. Okay, so you would notice here we have the sigma y, that is the yield strength, and right here the sigma u, this is the ultimate strength, and we have the rupture point right here. And for a low carbon steel, you would also have the yield point, or I mean the yield strength, and then here is the ultimate strength, and beyond that is the rupture point. Okay, so those are example of a ductile material. Now right here in figure 2.11, here is an example of a brittle material. So it's something like this, without much deformation or without much plastic deformation, and then it just go to fracture. Okay, so that's that's some of the examples of the stress strain curve. Okay, and another one I'd like to show is this typical properties of selected materials used in engineering. So it's a table wherein at least several materials that's commonly found or that's commonly used in engineering applications, and then here is the data for the ultimate strength and the yield strength, and as well as the modulus of elasticity and modulus of rigidity, and still some other data right here. Okay, so as you can see here that, for example, steel, there's actually many types of steel, like for example A36 steel, or grade 345, grade 450, and you would see here that it only has a tension, I mean a data for the ultimate strength in tension, and also the yield strength in tension as well. Okay, so for A36 it has a 250 megapascals, and the higher value, I mean the ultimate tensile strength is the 400. I mean the value is 400 megapascals. Okay, and let's say for a higher grade steel, let's say grade 450 of this type, it has a 450 tensile strength, I mean yield strength, and a 550 ultimate tensile strength. Okay, and if we have a stainless steel, then it has also values right here, and you would notice that they only have values in tension and not in compression. But for ductile materials, generally the tensile strength is almost the same as the compression strength, or maybe just maybe there might be some off values, but it can be, I think it can be assumed as they are equal or almost the same. But for right here, for example, a brittle material, cast iron, This is a brittle material, so it has ultimate strength in tension, and also ultimate strength in compression. And you would notice here, or you would see here, that the strength in compression is much greater than the strength in tension. Okay, so what else? We also have coppers and a lot more materials. Okay, so I guess that's all, and in the next video we'll be moving on to our next topic, which is stresses and strains for actually loaded members.